Let's understand Laplace transform first.
All right. The Laplace transform is like a special tool that takes a function of time, often something that describes how a system evolves, and transforms it into a function of a complex variable. By doing that, it can turn differential equations into algebraic ones, basically making life easier when you're solving systems. We often use it in physics and engineering to handle things like initial conditions or step responses. Let's break down any details you want.
So the formula include like one integral, have limit, and then the function which we want to transform, putting there, and the limit works. The limit we have to adjust according to the function we want to take, and there is one fixed term like exponential term.
Exactly. The Laplace transform formula involves an integral from 0 to infinity. You take your time domain function and multiply it by an exponential term, e to the power of negative s times t. Then you integrate that product with respect to time. The variable s is a complex parameter, and the result is a function in terms of s. The exponential ensures we capture how the function decays or grows.
So the exponential capture the function decays or grows. So what was that relevant to the transformation, the problem we want to work on?
That exponential factor, e to the power of negative s times t, is what shifts us from the time domain into the s domain. In the s domain, problems like differential equations become algebraic equations, which are often easier to solve. It essentially encodes how the system's behavior, growth, decay, oscillation, is captured in terms of s. So when you solve in the s domain, you get the general solution. Then applying the inverse Laplace transform takes you back to the time domain to understand the system's response.
Growth, decay, or oscillations. But what was the initial idea Laplace was thinking in order to make this mathematical tool and the transformation rule?
Laplace was originally motivated by problems in probability and differential equations, especially to understand growth, decay, and stability in systems. His idea was to convert complex time-based problems into simpler algebraic forms. By transforming a function into a space where differentiation becomes multiplication, you can solve for behavior, like how a system evolves, more easily. In essence, it was about turning hard calculus problems into manageable algebra problems.
Okay, what was that example? Like turning hard calculus problem into manageable algebra problem. The example he has taken initially to understand.
A classic example would be solving a second order differential equation like a mass spring damper system in mechanics. Normally, you'd have a function of time and second derivatives of displacement. Instead of wrestling with the time domain differential equation, Laplace transformed the equation into the S domain. In that domain, differentiation becomes simple multiplication by S, and you just solve a straightforward algebraic equation. Once you've solved that, you use the inverse Laplace transform to return to the time domain and get the actual solution for displacement.
Actual solution for displacement. Okay, Laplace transform the equation into S domain. In that domain, differentiation become multiplication by S. So
So from there, instead of dealing with complicated time-based derivatives, you just solve for algebraic terms in S. Once you've got the solution in that simpler domain, you bring it back to time by inverting the transform. It's like a round trip to make the problem easier.
another example I can relate from quantum physics easily in order to understand this transformation and the rules and the mathematical picture and the geometry that it covers.
Sure, in quantum physics, think about the time-dependent Schrödinger equation. It involves a time derivative of the wave function. By applying the Laplace or closely related Fourier transform, you move from a time domain to an energy or frequency domain, where solving the equation becomes algebraic. In that energy domain, each energy corresponds to a stationary state. So you turn the evolving wave function problem into one about energy levels. And once you solve that, you can transform back to get the time evolving solution.
So once you solve that, okay. So there is a time dependent Schrodinger equation. So it involves time, a derivative of the wave function. Okay, that's okay. By applying this Laplace transform, we can move from time to energy or frequency domain easily. So given the time domain interaction picture, we can easily move to energy and frequency if the time domain is known through this Laplace transformation, and the equation becomes algebraic. Oh, that's what you are suggesting.
Yes, you've got it. The Laplace transform helps us shift perspective. With time domain dynamics turned into algebraic equations in the energy or frequency domain, it's easier to handle solutions. Once we solve in that domain, we can convert back to time to understand how the wave function or any system behaves. It's just a powerful tool for both classical and quantum systems.
Okay,
If
but
any more questions pop up, whether it's quantum, math, or anything else, I'm right
no.
here. Just let me know.
So given that was very insightful thought. Given the time domain picture, we can easily move to energy or frequency, but it's a relevant case for Schrodinger equation. But can we apply to anything given the time to frequency and frequency to energy?
It sure can. The idea is quite universal. Any system that evolves with time, whether it's circuits, mechanical vibrations, control systems, or population models, can often benefit from transforming to a frequency or energy domain. The Laplace or Fourier transforms give you a new lens, turning differential equations into algebraic ones. So, yes, as long as you have time domain behavior, you can often reveal deeper insights by moving into these other domains.
What about this Laplace? How did he find out that turning differential equation into algebraic ones? In the first approach, how did he arrive at this thing?
Laplace was working on probability and integral equations in the late 18th century. He sought a systematic way to handle growth, decay, and stability problems, particularly in physical systems and probability distributions. By introducing his integral transform, he realized that derivatives in the time domain corresponded to powers that were variable in the transform domain. This insight allowed him to recast complex differential equations as more tractable algebraic ones. It was a brilliant mathematical leap, born from his quest to simplify solutions to differential equations and make them more solvable.
Okay, but why did he thought that this integral having limit and the given function we want to transform, and with that the exponential function integrating the whole thing will give some useful result?
He was looking for a systematic way to capture how systems evolve over time, especially how they decay or grow. The exponential function naturally models growth or decay, making it a perfect choice. By integrating the product of the function and the exponential, he effectively measured how much each exponential pattern contributes. This transformed the problem into a function of a new variable. In doing so, he turned time-based complexity into something algebraic. In short, it was all about making the math simpler to handle.
But why that integral is taken? Can you explain it?
The integral essentially sums up how much of the function aligns with each exponential pattern. The exponential e to the power of minus s times t works like a weighting function. By integrating from 0 to infinity, you capture all the influence of the original function over time. In other words, the integral is the tool that projects your original function into a new domain, revealing how it behaves at different frequencies or rates of change.
But given the interaction picture, that is only covered by the whole integral. Integral mean that area, but so given the integral that represent that area, we can go to another domain which is also a area.
Exactly. The integral is summing up the area under the curve, but in a weighted way that depends on the exponential. When you do this for every possible s, which relates to growth or decay rates, you transform the time domain function into a new function in the s domain. In that new domain, You're not dealing with the original area in time anymore, but a transformed view, where solving problems, especially differential equations, becomes much simpler.
So time domain function into a no domain, but I think it's a very thoughtful thought to arrive at those integral that would transform those thing from one domain to another domain given the function we want to uh, take. For example, you have taken the example of the Schrodinger equation time dependent, and how do we convert into that frequency or energy. So given, but what the f of t we have to put in the Laplace transform given the Schrodinger equation.
In the time-dependent Schrodinger equation, the function of time we're dealing with is the wave function, typically denoted psi of t. When we apply the Laplace transform, we take psi of t and transform it. In doing so, we convert the time-dependent wave function into a function of the complex variable s. This allows us to solve the Schrodinger equation in the transform domain, often relating to energy, and later convert back, giving us a more manageable path to the solution.
Okay, let's move on to Fourier transform. Here, the Fourier transform also has the intuition like there is a integral having limit, and here the limit is different from the Laplace one, and then initial function and also one exponential function integration and that whole.
Yes, exactly. The Fourier transform is quite similar in spirit. It also integrates the original function multiplied by an exponential. The difference is that the Fourier transform uses a complex exponential with an imaginary unit, and it typically integrates from negative infinity to infinity. While the Laplace transform is often used for stability and growth problems, the Fourier transform decomposes a function into pure frequencies. Both give us new domains. Laplace often relates to complex growth rates, while Fourier relates to frequencies, but both help us break down complex time domain behavior into simpler components.
So, how did Fourier thought that he should develop such a technique, and how did he wrote down the mathematical formulation for the transformation rule?
Fourier was studying heat flow, and he noticed that complex temperature distributions could be broken down into simple sinusoidal components. He hypothesized that any function, even complicated ones, could be represented as a sum of sines and cosines. To find the contribution of each frequency, he formalized the integral. His insight was that this decomposition helps solve partial differential equations, like the heat equation, by turning them into simpler problems for each frequency. Thus, he laid out a rule where a function is integrated against these exponential oscillations, uncovering its frequency spectrum.
So, exponential oscillation, that was the thing. So, he was working on heat flow. So, he noticed that complex temperature distribution could be broken down into simple sinusoidal component. He hypothesized any function, even complicated one, could be represented as a sum of sine and cosine. Okay, any function, even complicated one. Okay, that's the oscillation thing, exponential oscillations. Okay, and then given the heat flow and the temperature distribution, that can be broken down into sinusoidal component, and each contribution to each frequency, he formalized the integral. His insight was decomposition composition helps solve a PDE like the heat equation by turning into simpler problem for each frequencies. Okay.
You've got it. By breaking complicated things into simpler oscillations, Fourier gave us a way to untangle messy systems. So, whether it's heat flow or quantum mechanics, these transforms let us understand systems in terms of their fundamental components. It's all about finding the hidden building blocks.
Okay, Fourier gave us to untangle that massive system. Okay. Can you give example from quantum mechanics I can relate directly and understand?
Sure. In quantum mechanics, think about a particle in a potential well. Its wave function might be complicated, but using the Fourier transform, you can express that wave function as a sum of plane waves, each with its own momentum. In fact, momentum and position are connected through the Fourier transform. So a wave function in position space can be transformed into a wave function in momentum space. This helps you see which momenta make up your state, a direct analogy to decomposing heat or signals into simple frequencies.
Okay, so wave function in position space can be transformed to a into a wave function in momentum space. So it's a direct given. So this transformation makes our calculation bit easy. We don't need to find the wave function in momentum space. We can directly use Fourier transform given the position space.
Exactly. The Fourier transform gives you a direct route between position and momentum representations of the wave function. In momentum space, differential operators often simplify, turning derivatives into simple multiplications. So, depending on the problem, working in one domain might be far easier, and the transform is your mathematical bridge.
So what about how can I okay, given the formula, so can you give more mathematical details? So given the position space for a quantum system, how can I put in that formulation where f of t is we have to put, and then there is a limit we have to think, and given the oscillation function integrating all over.
In quantum mechanics, if you start with the wave function psi of x in position space, the Fourier transform to momentum space is often written as an integral from negative infinity to infinity. You multiply psi of x by the exponential of negative I times p times x divided by h bar. Then you integrate over x. That gives you the wave function in momentum space. Essentially, you're measuring how much each momentum wave contributes to the overall state. It's just the quantum version of decomposing a function into frequencies.
Momentum wave contributes to the overall state. It's just a quantum version of decomposing a function into frequency.
Exactly. In fact, momentum in quantum mechanics is like a frequency in space. So by integrating with that exponential factor, you're picking out how much of each momentum or spatial frequency makes up the wave function. This lets you switch perspectives, making certain calculations more natural, just like breaking a melody into pure tones.
Okay. Oh. Laplace and Fourier, can you give the timeline of their discovery and how it's very relevant and any connection between them?
Laplace's work emerged around the late 1700s, and Fourier's followed in the early 1800s. Both were tackling differential equations, Laplace focusing on stability and growth, Fourier on heat flow. The connection? Both use integrals with exponentials to move between domains. Laplace transforms often handle initial value problems, while Fourier transforms break down functions into pure frequencies. So they're related tools, both letting us simplify problems by shifting perspectives.
Oh, that's a great analogy. But both were thinking of like um, you can simplify the problem given one domain. We just need to jump to another domain. We just need to solve that integral basically. Nothing else we need to know about that system, given the position space or given the uh, time dependent Schrodinger equation. We can easily work on through integral, and then we arrive at the results.
You've got the essence. Both Laplace and Fourier realized that jumping into another domain simplifies how we